Problem 23 is another optimization problem. So we're given a cylinder and its volume. So this is one of our constraints that we know. And we're asked to minimize the total surface area and then find the corresponding height and radius at that minimized surface area. So for an optimization problem, that means the equation that we're going to have to build and then take a derivative of is surface area. Some other things we probably should take note of is the volume equation for a cylinder, which is pi r squared times h, and then the surface area equation, which is 2 pi r squared plus 2 pi rh. And it's worth noting that this is because it includes the top and bottom of the can that we have that longer two-part equation. If it did not include the top and bottom of the can, it wouldn't have both those segments. So next, we want to be able to find a way to simplify this equation so we can take the derivative of it. So we have two variables in here, and we don't want to take a partial differential. So that means somehow we're going to have to turn a radius into a height or height into a radius. And we're going to use these two constraints that we were given. So if we know volume equals 400 centimeters cubed, that also equals pi r squared times h. We can actually solve for height, and that will give us 400 divided by pi r squared. And we can plug that in to our surface area equation, giving us just one variable to work with. So now we have surface area equals 2 pi r squared plus 2 pi r times 400 over pi r squared. Now you could have done this for either variable. You could have solved for r and plugged in, swapped out the r's from the surface area equation. I think this is simpler because there was only one height factor in that equation originally, and it has less substitutions for you. So if we simplify this, we get 2 pi r squared plus 800 over r. If we take the derivative of this equation, we are going to get 4 pi r plus, minus 800 r squared. And now from this point, we want to set this equation equal to 0. If we set this to 0, we're going to get 4 pi r minus 800 over r squared, and then you're simply going to solve for radius at this point. When you solve for radius, you're going to get the cubed root of 200 over pi, and then the last thing we need to do is solve for height. So if we go back to the height equation that we made, we have h equals 400 over pi r squared, and if you plug in, you're going to get 400 over pi times 200 over pi to the 2/3. And we can simplify this a few steps. If you get h equals 400, simplify the pi, you're going to get pi to the 1/3 times 200 to the 2/3. You can pull out a 2, giving you 200 over pi to the 1/3 over 200 to the 2/3. Simplify this another step, and you get 2 times 200 over pi to the 1/3, leaving you with a height of 2 to the cubed root of 200 over pi. And these are the two dimensions that will give us the minimum surface area of our cylinder. Problem 24 is a probability question. So the situation you're in is you're in an airplane that has two engines. Each of those engines has a 10% chance of failure, and it wants to know what the likelihood is that you'll have a safe flight without either engine failing. So your left engine has a 1 in 10 chance of failure and a 9 in 10 chance of success. Your right engine has a 1 in 10 chance of failure and the same 9 in 10 chance of success. So essentially, what this wants to know is what's the likelihood of both these 9 in 10 chances of happening. What you do in this situation is you just simply multiply. So you have 9 times 10 times 9 over 10 equals 81 over 100, which equals 81% chance of success. So this is the double success situation. And that's the answer to the problem. A common mistake that people make is they read this problem and they say, okay, so 1 over 10 chance of failure. There's two 1 over 10 chances of each engine. So that's a 2 over 10 chance that they both fail. Therefore, I have an 80% chance of success if they just take the reciprocal of that fraction. That's incorrect. You multiply probability in a simple probability question like this. A good way to check if you've done this correctly is to make sure that all of your situations, all possible situations, should equal 100%. So say we have a left engine success but a right engine failure situation. That is going to be 9 over 10 times 1 over 10, giving us 9 over 100. So there's a 9% chance that the left engine succeeds while the right one doesn't. And then the other situation, the third situation we can go into is left engine fails, right engine succeeds. This is going to be the identical situation, but in the inverse, with a 9% chance of happening. And then the horrible situation where both your engines fail is going to be 1 over 10 times 1 over 10 equals 1 over 100. So there's a 1% chance that happens. And if you add these numbers up, you're going to get 100%. So it is a 100% chance that something happens, which is a good way to check if this problem's done correctly.